All right, folks, I hope you're all doing well. During this session, within our sort of introductory material heading for the Laplace Transform, we're going to carry on our discussion about ordinary differential equations. Last time we talked about first-order linear ordinary differential equations, and this time we're going to focus on second-order linear ordinary differential equations. So the general form that we're going to have is a of x onto y double dot plus b of x onto y dot plus c of x onto y equals d of x. Now, sort of what we had before, if you recall, we had functions of x, p, and q for our first order differential equation, and now we have four functions of x. We have a of x, b of x, c of x, and d of x. And again, those are functions of x. They can also be constants, which are functions of x. They could even be zero, but they cannot contain y's inside those expressions. The y's live here. We have the second derivative of y, first derivative of y, and y itself. So, as you might expect, the solution to the differential equation has to be the function y equals f of x that satisfies the second order differential equation expression. If you recall, for the first order equations, we had this concept of a homogeneous equation where the right hand side essentially was zero, and we have the same thing here. So if we have d of x equal to 0, then what that means is we have a homogeneous, or sometimes we say homogeneous, second order linear differential equation. Okay, so linearity buys us a couple of very important things. So first of all, if f of x is a solution to the differential equation, and I need to write that properly, and we also have that g of x is another solution to the differential equation, because the solutions don't have to be unique, then it turns out that the sum f of x plus g of x is also a general solution to the differential equation. Okay, so that's an important result, and we're not going to prove it or anything, but it's not really too bad to prove. So anyway, going on, another important result that we have due to linearity is that if f of x is a solution to the differential equation, then it turns out that any scalar multiple of that function is also a solution. So k times f of x is also a solution to the differential equation. So again, that is an important facet for what we're going to be getting into in terms of deriving the solutions in general that we're going to have to the differential equation. Okay, so as an example, let's consider this second order linear homogeneous differential equation. And it has, in this case, constant coefficients, right? The coefficient on y double dot is 1. It's implicitly there. The coefficient on y dot is 5. The coefficient on y is 4. And then we have 0 on the right-hand side, which makes it a homogeneous equation. So we want to think about what is a potential solution for this differential equation. So if you recall from our discussion on first order systems, we said you can kind of just sit back and maybe guess at a solution. Now that guess isn't completely in the dark. It's actually going to require some intuition. So in this case, we're going to suppose that a solution we're going to consider is y equals e to the ax, where a is just some real constant value. Okay, so then if we have that, we take the first derivative of that, we know that y dot equals AE to the AX. And then we also know that the second derivative, y double dot, equals a squared e to the ax. Okay, so now we're going to write our differential equation by plugging in those terms that we just created. So y double dot, we'll write that first. So we're going to write a squared e to the ax, and then plus 5 onto ae to the ax, and then plus 4 on our y term, which is e to the ax. And that equals 0. With that presumed solution, we have to look what has to happen here in order for that expression to be satisfied. So essentially, when does y e to the ax actually hold? First of all, we notice that we can factor out an e to the ax on the left-hand side. So we're going to write our e to the ax, and then that's going to be multiplied by something that looks like just a squared plus 5a plus 4, right? And then we close that, and that's going to still equal 0. Now let's think about the terms that we have here. So first of all, this e to the ax term, well, there is no value of a or x that would make that 0. So the only way that the expression on the left-hand side can equal 0 is if this expression, this polynomial that's in the brackets, equals 0. Well, when can that happen? Well, that only happens when the value of a is a root of that polynomial. Because remember, the roots of the polynomial are the values of the independent variable, so to speak, when the polynomial becomes 0. Now, something of interest is this polynomial in here is called the characteristic polynomial. And as we just discussed, it has a lot to do with the roots of that polynomial have a lot to do with the solution to the differential equation. Okay, so if we solve for the roots of this differential equation, we're going to get that we can actually factor this, if we want, as a plus 1 onto a plus 4. Okay, and that's going to lead to roots of a equals -1 or -4. Okay, so if a has a value of -1, then this polynomial will evaluate to 0, or if it has a value of -4, then this polynomial will evaluate to 0. Okay, so here I've rewritten the differential equation and the characteristic equation. The characteristic polynomial was the polynomial expression on the left-hand side. That was the a squared plus 5a plus 4. And if we set that equal to 0, we have an equation, and that's the characteristic equation. And then we also have that the roots of that equation are going to be -1 and -4. So those roots lead us to two different expressions. So we're going to say y1 equals e to the -1x. That's one solution. And y2 is going to be e to the -4x. And we want to plug those in and try them out just to make sure that that works. And it's pretty obvious that it does because of the buildup for the characteristic polynomial, the characteristic equation. But we'll go ahead and work this out anyways. Okay, so now we're going to plug these in and see what we get. So first of all, we have y1, so now I'm going to compute y1 dot. So y1 dot, right, it's just going to be -1 e to the -1x. I'm just going to write that as -e to the -x. I won't write the 1 explicitly. And then I'm going to talk about y1 double dot. Well, I'm just going to bring down another 1 again, so I'm going to get back to e to the -x, right? And then I'm going to do the same thing for the y2. So y2 dot equals -4 e to the -4x, and y2 double dot is equal to 16 e to the -4x. Okay, so I have these terms to work with, and so I'm going to use the y1 terms and plug them into the differential equation and see what I get. Okay, so I'm going to just mark this as 1 for solution 1. So I'm going to plug in y1 double dot for that. So I'm going to have e to the minus x, e to the minus x, plus 5 times y1 dot, which is negative e to the minus x. Let me write that just a little bit better. Negative e to the negative x, right? And then plus 4 times the original expression y1, which is just e to the negative x. Well, I can tell by inspection that I'm going to have 4 times e to the negative x plus 1 times e to the negative x. That's 5e to the negative x. And then I'm going to add to that negative 5e to the negative x. So it's pretty obvious that that does in fact equal 0. So therefore we know that y1 equal to e to the negative x is a solution to that differential equation. Right, so let's look at number 2. Right, so solution 2, I'm going to have the second derivative is 16 e to the negative 4x, and then plus 5 times the first derivative, which is negative 4 e to the negative 4x, and then plus 4 e to the negative 4x. So it might not be quite as obvious, but it's pretty close. I have a positive 16 here times e to the negative 4x plus another 4, so that's going to be 20 e to the negative 4x, and I'm going to subtract 20 times e to the negative 4x. So that's going to also give me 0. So I know that the solution given by y2 equals e to the negative 4x also satisfies that differential equation. So we have found 2 solutions to that equation. For this linear second-order homogeneous differential equation, I found 2 solutions. y1 equals e to the negative x, and y2 equals e to the negative 4x. So because it's a linear differential equation, I know that I can actually take the sum of those two and have a solution. So I also know that I have a solution that maybe is a little bit more general, but that's going to be y1 plus y2, okay? And so that's going to be e to the minus x plus e to the minus 4x, okay? So we know that because it's a linear differential equation. And I also know that any scalar multiples, right? So I also know another solution would be some constant, we'll call it C1 times Y1 equals C1 e to the minus x. We know that because any constant multiple of a solution is also a solution, again, due to linearity. And similarly, we know that C2 onto Y2, which is going to be C2 e to the minus 4x, is also a solution. And from all of that, we arrive at a statement we can make that says, well, if that's the case, then we can make a very general solution. And we're going to call this the general solution. The general solution is going to be something that looks like y equals C1 e to the minus x plus C2 e to the minus 4x. So that is the general form of the solution to that second order linear differential equation. And of course you may say, great, so what? What can I do with that? Because what are C1 and C2? Well, it turns out they can be anything, at least any real number, any constant real number for C1 and another real number for C2 is going to satisfy the differential equation. But if I need to know something a little more specific, let's say I have a initial conditions, right? So I have this function y. Y has, I can plot y versus x. And so if I'm looking for a particular solution, I'm going to have to put some constraints on what C1 and C2 are. Okay, so how might I do that? So these constraints are going to come in the form generally of something we call initial conditions. So I'm going to call these initial conditions, I'll say initial conditions on the solution, and that's going to be, for example, we'll say y of 0 equals 5. Now that's something that has to be specified. Okay, you can't pull that out and say, well, y of 0 has to be 5. That's something that does have to be specified in essentially in the sort of the problem statement. And also, let's say that at the first derivative, y dot also evaluated at 0, at x equals 0, equals 8. Okay, so now I've just made those up, but those are the constraints we're going to put, or the initial conditions we're going to put on the problem. So what does that mean? Well, if we're going to evaluate y under these conditions, right? So if I want to look for the value of y itself, y of 0 equals c1 e to the minus 0 plus c2 e to the minus 40, right? I better make that so it doesn't look like 4 times 0, right? So it doesn't look like a 40. All right, so now I know that e to the 0 power is 1, so this is just going to go away and become a 1, and so is this. So that's going to be a 1. So this is just going to evaluate to c1 plus c2 equals 5. Well, there is a linear equation with two unknowns. So if you're thinking ahead, I'm going to do the same thing with the first derivative. So y dot of 0 is going to be, well, first of all, what is the first derivative? Actually, let's go ahead and do that first, just for a little bit of clarity. So I'm just going to say y dot of x in general, just so I can write it out. So it's going to be negative c1 e to the minus x minus 4c2 e to the minus 4x, right? So then I can plug in x equals 0, right? So x equals 0, so I'll get y dot of 0 equals negative c1 minus 4c2, and that's going to equal 8, right? Because if I plug in 0 again, e to the minus 0 is 1, e to the minus 4 times 0 is 1, so I just get negative c1 minus 4c2, and so that is another equation with two unknowns in it. And so now I can solve that equation, right? I get two equations and two unknowns, and I can solve for the values of c1 and c2 just using normal algebraic techniques. And so I'm going to come up with c1 is equal to 28 over 3, and c2 is equal to negative 13 over 3. Okay, and you say, well, what do I do with that? Well, now, with these conditions that are specified here, I arrive at these two values for C1 and C2, which we would then plug in C1 and C2 here and here. So I get the specific, or the particular solution is the thing that we would call it. Okay, so for those initial conditions, I had C1 equal to 28 over 3 and C2 equal to negative 13 over 3. So the particular solution for the differential equation is going to be y equals 28 over 3 e to the minus x minus 13 over 3 e to the minus 4x. Okay, so that is the particular solution to the differential equation that we had. It's based on the general solution, and we need two constraints in order to solve for the two unknowns that we had, C1 and C2. Okay, for the example that we just worked, the roots that we found for the characteristic polynomial were what we call real and distinct. Okay, so when the roots are real and distinct, right, so we're going to say that we have roots that are R1 and R2, and R1 is not equal to R2. Okay, so they're real, right? So they're real valued. Then we had the general solution was something that looked like y equals C1 e to the R1x plus C2 e to the R2x. Okay, that is the general solution in that case. Okay, so the next case is what happens when the roots are real and equal. Okay, so what we mean is we have roots that are R1 equals R2, and we're just going to say that equals R. It's just a single real number. In that case, we're going to have the general solution is y equals C1 e to the Rx plus C2 times x e to the Rx. Okay, so we have this x term here. And we're not going to prove why this works this way, but essentially that structure will work as a solution to the differential equation, and but it also lets us set up with our initial conditions something that lets us solve for two different constants here, so to produce a particular solution when we do have initial condition constraints. Okay, we want to look at an example where we have real and equal roots. So we have this example here where we have y double dot plus 6y dot plus 9y equals 0. All right, so we know that we can write the characteristic equation for this essentially by inspection. So we can get r squared plus 6r plus 9 equals 0, which we know we can factor as r plus 3 onto r plus 3, which means that our roots are going to be r equals -3 and -3. So we have a pair of real repeated roots. Okay, so we can write the general form of the solution pretty much by inspection. We can just say that y equals C1 e to the minus 3x plus C2 x e to the minus 3x. Okay, so again, we don't want to forget that we have this x term this in the second expression. Okay, so that is the general solution, but we want to go for a specific solution. So now we just got to create some initial condition examples. But before we do that, we're going to go ahead and compute the first derivative. Okay, so just because we're going to need that in our expression. So let's go ahead and write out what y prime is. So y prime is going to be, well, the first term here, we just bring down the exponent coefficient, so we get -3 onto C1 e to the minus 3x. And then the second term, we got to use the product rule here, so I'm going to keep the C2 outside, but in the parentheses, right, I've got to take the derivative of this product. So the first one, I'm going to take the derivative of the first term times the second. So the derivative of x is just 1, so I'll just have e to the minus 3x, and then plus the first term times the derivative of the second. So that's x times -3 e to the minus x. Okay, so I can go ahead and rewrite that, just clean it up a little bit. So that's going to be -3 c1 e to the -3x plus c2 e to the -3x, and then inside here I'm just going to write 1 minus 3x. Okay, so if I collect things together, I should get something that looks like that. Right, so that's the first derivative of our general solution. So now I'm going to apply some initial conditions. So let's say that I have y of 0 equals 2. Okay, well, if I plug in 0 for x in my expression for y, then because I have this 0 here, the second term entirely vanishes, and the first one is just going to be c1 e to the 0 power, so it's just going to be c1. So I know right off the bat that c1 equals 2. So that's pretty convenient. And then for the second one, if I plug in x equals 0, well, again, the e to the negative 3x term, so this term here is going to turn to 1. This term is going to turn to 1. And this term is going to go away. So I'm just going to have negative 3c1 plus c2. So I'm going to say y prime of 0 equals negative 3c1 plus c2. And that equals, let's say we were given that equals 3. Okay, so what I have then is that's going to be equals negative 3 onto 2 plus c2 equals 3. And we see from that c2 equals 9. All right, so now we can actually write the particular solution to this differential equation, right? So we had the conditions that y of 0 equals 2 and y prime of 0 equals 3. All right, so the particular solution under those conditions is yp, we'll say for the particular solution, equals c1 is 2, so we'd have 2e to the minus 3x, and then plus c2x, so plus 9x e to the minus 3x. All right, so that is going to be the particular solution to the given differential equation with the given initial conditions. Okay, so now we want to discuss what happens in the situation where the roots are complex for the characteristic equation. So obviously initially we had real and distinct roots, and then we talked about real and repeated roots, and then it turns out that for a second order linear differential equation with constant coefficients that are real valued, we will have we can have complex roots, and if the roots are complex, they will appear as a conjugate pair. So as a conjugate pair, right? So why do we know this is going to be the case? Well, suppose our characteristic polynomial looks like AR squared plus BR plus C, right? And then we're going to have that equal to 0, right? And we know using the quadratic formula that we can solve that, and we're going to have our roots are going to be negative b over 2a, right, plus or minus the square root of b squared minus 4ac divided by 2a. Okay, so that should be no surprise to you. So let's take a little bit closer look at what's going on with this quadratic formula. So if we look at the term under the square root, right, so we're going to have three cases that can occur. One of them is going to be that b squared minus 4ac, that quantity is greater than 0. And that's going to lead to our real distinct roots, right? Because we're going to have some term here, negative b over 2a, plus or minus the square root of something that is real. Okay, b squared minus 4ac being greater than 0 means that square root, that's going to work out. It's not going to give us a complex number, and so we're going to have real and distinct roots that are going to be some number plus or minus some other number. Okay, so there's going to be real distinct roots. The next case is going to be when b squared minus 4ac equals 0, and that's when we're going to have our repeated roots. Okay, they're still going to be real valued, because when b squared minus 4ac equals 0, this entire expression here goes away, and all we're left with is negative b over 2a plus or minus 0. Okay, so that's going to give us two roots that are equal, both of them, to negative b over 2a. All right, and then the third condition is going to be when b squared minus 4ac is less than 0, and that's where we're going to have a conjugate pair, right? So we're going to have a conjugate, let me spell that right, a conjugate pair, right? And so a lot of textbooks are going to write that, if you look at it, we're going to have a lambda plus or minus j mu, okay, where lambda is going to be equal to the negative b over 2a term, right? So that's going to be this. And then mu is going to be equal to essentially the magnitude of the square root of b squared minus 4ac over the quantity 2a. Okay, so, or the absolute value of that. All right, so that's where these lambda and mu terms. So we're going to have a complex conjugate pair of roots that look like lambda plus or minus j mu. Okay, so when we have that condition where we have a complex conjugate pair of roots that are written as r equals lambda plus or minus j mu, well, we're going to write the general solution in a similar fashion that we did before for the distinct roots, but it's going to have a little bit different form. So we're going to say y sub g, the general solution, is going to be c1 onto e to the exponent. Now is going to be a complex number, so it's going to be e to the lambda plus j mu onto x, and then plus c2 e to the quantity lambda minus j mu onto x. Okay, so again, we're just plugging in the roots up here, right? Let me underline that. So that's one of the roots, and that's the other root. Okay, so we just have a c1 e to the something times x plus c2 e to the something else times x. Okay, but it's just now that these exponents are both complex numbers, and again, they're a complex conjugate pair. So now what can I do with that? Well, I can use the rules we have for exponents, so I'm going to rewrite this as c1 e to the lambda x times e to the j mu x. Okay, so that's what I'm going to do with the first term, and then plus c2 e to the lambda x times e to the negative j mu x. Okay, so all I've done is separated this exponent that was a sum into terms that I multiply, and did the same for both halves of that expression. And then I can factor out the e to the lambda x. So I'm going to have e to the lambda x onto something that looks like c1 e to the j mu x plus c2 e to the minus j mu x. Okay, now remember the c1 and c2 are just real numbers, and they're certainly not necessarily the same. Okay, so now we want to pull something out of our memory. If you remember from Euler, from Leonhard Euler, we had something that said e to the j theta, right? So e to the j theta, that's the complex exponential, can be written as cosine of theta plus j times the sine of theta for some angle theta. Okay, so that's an important thing to note. So we're going to use that e to the j theta concept here in our e to the j mu x and our e to the minus j mu x. Okay, so when I do this, I'm going to end up with an expression that's going to be fairly long. So I'm going to try to fit it on here in a reasonable way. So I'm going to, again, have this, we're still talking about the general solution. So I have y of g equals, or y sub g, I should say, is e to the lambda x. Okay, and then we're still dealing with things inside. We're going to convert all these things from complex exponentials to sine and cosine terms. Okay, so I'm going to have a C1. Well, the first thing we're going to do is apply Euler's rule here, Euler's formula, to the e to the j mu x. And so I'm going to write that as cosine of mu x plus j sine of mu x. All right, and then I've got to deal with the C2 term. So I'm going to just write that underneath here, plus C2 times the cosine of minus mu x plus j times the sine of minus mu x, right? And so that was all multiplying the C2 term, and then I close my brackets. So that's a lot going on there. Okay, so now we're going to take advantage of the fact that cosine is an even function. That means that the cosine of negative theta equals cosine of theta. And we're also going to take advantage of the fact that sine is an odd function. So that is the sine of negative theta equals negative sine of theta. Right? So we're going to use those, both of those here and here. So we're going to, again, rewrite our expression a little differently. Our general solution, y sub g equals e to the lambda x. And that's going to be C1 onto cosine mu of x plus j sine mu of x. Okay, that's our C1 term. And then plus C2, and now we're going to write cosine of mu of x, and then minus j sine mu of x. Okay, so now I'm just going to collect terms and rearrange a little bit. So I'll have e to the lambda x, that's still on the outside here. And now I'm just going to take this cosine mu x term and this cosine mu x term, bring them together. So I'm going to have a C1 plus C2 onto the cosine of mu x. And then I'm going to do something similar with the sine term, but I do have to deal with this negative here. So I'm going to have plus j C1 minus C2 onto the sine of mu x. Okay, so I've reduced this down a little bit, and now I'm going to make a substitution here. So for the C1 plus C2, right, so I have this thing here. I'm going to just call this some other constant K1. Okay, and then for the j times the quantity C1 minus C2, I'm going to call that K2, because remember, as we go along here, these C1 and C2 terms are just arbitrary constants, right? They become fixed when we have a particular solution, but from a general perspective, we can just lump those together and sort of rename them because they're still just arbitrary constants. And it actually turns out that they can also be complex themselves. Okay, so it's okay for me to pull this j inside of K2. All right, and so that gives us a general form here that we would say, well, I have that general form is going to be equal e to the lambda x times K1 cosine mu x plus K2 sine of mu x. Okay, so the things that are important to know, first the K1 and the K2 terms, again, are arbitrary. And then we have lambda here, which comes from our complex conjugate pair of roots, and we have mu here, which comes from our complex conjugate pair of roots. So everything's accounted for in here, and we've used a little bit of trig work using Euler's relationship to come up with a convenient form for the general solution to a second order linear homogeneous differential equation when we have constant real coefficients on the actual differential equation, and so we get this nice trigonometric form that has a complex exponent, or I'm sorry, an exponential in front of it, not a complex exponential. All right, so that is the general form. So now we just need initial conditions if we want to specify specifically what K1 and K2 are. Okay, so we're going to work an example here. So this one is y double dot plus 4y dot plus 5y equals 0. So that's the differential equation. Again, we have constant coefficients here. They're real valued. It's a homogeneous second order linear differential equation. The right-hand side term there is 0. And we also have initial conditions specified. It says y of 0 equals 0, and the derivative of the function at 0 is equal to 3. All right, so first of all, we're going to look at the characteristic equation. So the characteristic equation is going to be r squared plus 4r plus 5 equals 0. And so if we want to write it out in detail, we're going to say that our A equals 1, B equals 4, and C equals 5. That's the coefficients of the characteristic equation. So our R is going to be negative B over 2A plus or minus the square root of B squared minus 4AC, all divided by 2A there. And so that's going to be negative 4 divided by 2 plus or minus the square root of 16 minus 20, and that quantity also divided by 2. And when we work that out, that's going to be equal to negative 2 plus or minus J1. Okay, so from that we're going to have lambda equals negative 2 and mu equals 1. All right, so now we can write essentially by inspection the general solution. So our general solution is going to be y sub g. Our general solution is going to be e to the minus 2x, right? That's an e to the lambda x. And it's going to be onto some constant k1 times the cosine of mu x. Well, mu is just 1, so I'll go ahead and write it in there, 1x, just so you can see that it is there, right? And then plus k2 times the sine of 1x. Okay, so that is our general solution. Okay, so now we'll go another step further. We'll look at the derivative of this, right? So y prime of the general solution is going to be, well, now I've got this product thing going on again, right? So I've got to have something that looks like the derivative of this times that expression, right? So the derivative of this is going to be minus 2e to the minus 2x onto k1 cosine of x plus k2 sine of x. All right, so that's the first part of the derivative. And then, so that was the derivative of the first term times the second plus the first times the derivative of the second. Right, so plus e to the minus 2x times the derivative of the second. So the derivative of the cosine is going to be negative sine, so I'm going to have negative k1 times the sine of x, and then derivative of sine is cosine, so I'll have plus k2 times the cosine of x. Okay, so all of a sudden I've got something rather large going on here. Okay, so now I'm going to use my initial conditions to solve for what k1 and k2 are. So first we had the initial condition that was y of 0 equals 0. So I'm going to say yg of 0 equals 0. And to get that, I'm going to plug in zeros for the x terms in the general solution. So I'm going to plug a 0 in here, I'm going to plug a 0 in here, and a 0 in here. So e to the 0 power is just a 1, so I'm going to go ahead and write that as a 1 just to show that it's there. And then the cosine of 0 is going to be 1, and the sine of 0 is going to be 0. So the sine term is going to go to 0. It's going to eliminate k2. So all I'm going to do is have a k1 times 1 in here. So k1. And so what that tells me is k1 actually equals 0 in this case. Okay, so now we're going to look at the initial condition on the derivative. And so that is y dot sub g of 0 equals 3. So what I need to do is plug in zeros here, 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 and here. So the bookkeeping, you want to be careful about some things here. But when I do that, I am going to get something that looks like, well, e to the 0 is 1 out front, and then I've got this negative 2 coefficient. So it's going to be negative 2 onto, and by the way, I already know k1 equals 0, so I can eliminate k1. I know the sine of 0 terms are going to go away, so that's going to go away to 0. That's going to go away to 0. The k1 term is already, we know that's 0, so I'm going to have negative 2 onto something that looks like a 0, right? And then plus 1 onto something that looks like 0 plus k2 times 1. So I got a k2 here, and that's going to be equal to k2. Okay, so again, so I know k2 equals 3 from that. So when the dust settles, assuming I haven't made a calculus or an algebra error in this derivation, we're going to have the particular solution. Y sub p is going to be e to the minus 2x onto, well, I had k1 equals 0, so the cosine term is gone, and I'm just going to have 3 times the sine of x. Okay, and so I can write that a little differently. I can just say that's going to be 3 e to the minus 2x times the sine of x. So that is the solution to that linear second order homogeneous differential equation. We have real coefficients. I do want to emphasize that when the coefficients are real, and you have complex roots to the characteristic equation, when the coefficients are real, those roots must appear in complex conjugate pairs, which is the case we handled in this particular example. All right, so now you should be able to solve second order linear homogeneous differential equations. Doesn't mean that the calculus and the math and everything is always going to be easy, but you should be able to solve those equations for any of those structures there. All right, so we will continue. Our next little segment will involve linear second order differential equations that aren't homogeneous. So we're going to have a right-hand side term. So there's going to be a little bit of work we have to develop to do the solutions for that. But we've had enough time in this session, so look forward to that in a second session. And then we're going to be able to talk about the Laplace transform, and hopefully with all this differential equation discussion, it will be clear to you why we want to use the Laplace transform and how that it can make our lives easier. So thanks for listening, and I hope you have a good rest of your day.